Welcome to this module in the Big Data Analytics Summer School on random forests and their application to space exploration, specifically for flyby science. My name is Thomas Fuchs. I'm a research technologist at JPL, and that's a real-world example which we're actually going to use for future flybys. So flyby science in general is difficult. So nowadays, a lot of space probes fly by asteroids or comets on their way to their primary goal. For example, the Juno mission or a deep space mission flew by asteroids, and during a flyby, there's a very limited amount of time to take pictures and measurements from these highly interesting objects. So these targets have a very diverse morphology and a very diverse composition, which we're actually interested in. Then their target location is not known beforehand. A good example is current Rosetta mission, where it actually turned out that it's a more or less two-body object. Also the geometry and the illumination constraints are not known beforehand. So, and the features of interest are very often highly localized. So you could imagine if you visit a moon of Jupiter, for example, you can plan all the stellar orbital mechanics beforehand, because you exactly know where this object is going to be. You know where to point your camera's instrument beforehand. That's not the case in these flyby missions for these kinds of asteroids and comets. So there are examples from the past, like the flyby at the asteroid Matilda, where the current methods to track these asteroids actually failed. So you can see here a image sequence from the flyby at Matilda, and you can see in the center that it actually fell out of the frame of the camera completely. So that's naturally a huge loss for science, and also if you have more advanced probes, if you want to point, for example, a spectrometer, you couldn't even find the object. So there is a motivation to have a new approach to these flyby science experiments. So the status quo is that the probes are far away from Earth, approaching one of these asteroids. The light gap could be huge, could be hours, for example, and every command has to be entered from Earth. Every correction command, every command for pointing cameras. So the left side describes the current status quo. So what we want to do in the long run is actually to have more autonomy on these probes. So we want to have onboard computer vision using random forests, for example, to track these asteroids over time, find interesting surface features, and then automatically point instruments at these surface features during these very short flybys. So, and in the long run, such procedures could significantly increase the science gain for flyby missions. In practice, from a computer vision standpoint, what we present here is a setup where we do feature extraction. We use something like local binary patterns, which can describe texture around points of interest. We use mean shift procedures to actually find modes in our accumulator images. Then we use median filters for edge preserving constants. And then we also use integral images to very quickly extract features like half features, for example. In addition, we use 3D histograms of color if color is present. Quite often it's not. And then also other transformation approaches before we actually go to the machine learning side and then use random forests to classify objects. So here we actually see images from Hartley 2, an active comet, from a flyby mission. At the top left, you see the original image. At the top right, you see surface features which were marked by a domain expert. So a planetary scientist marked the features of interest which could be interested for example, spectrometer measurement or something else. And on the bottom image, we see red crosses, which are proposal detections of the algorithm, where you can see which most of the time hit actually the points of interest, but have a lot of false positive. So and what we want to do is we want to use random forests as a classifier to weed out good detections from bad detections to highly increase the science return. So our goal is pattern recognition. So these surface features, these bright surface features, are interesting because they can actually reveal the the material the asteroid, for example, is actually made of, because most of the time the material is covered by dust or some kind of regolith. So the problem is these features can be very diverse, as you can see on the right side. For different kinds of objects, they could be very faint or very prominent. Sometimes they look like refractions of a crater, and so on. So our pattern recognition approach is as follows. So at A, you can see the original image. What we do then is we apply a median filter, which nicely finds high albedo areas, so very bright areas in the image. A median filter is useful for this step because it's actually edge preserving. So we apply the median filter, subtract it from the original image, which ends up as image B, where you can see these bright spots. So the spots we find here are too many. They include the points of interest, but also include a lot of false positives. So what we do then is we run a mean shift procedure, which is a clustering algorithm presented in a different module, which finds actually the peaks in this map. So we end up with detections of these high albedo features, which are the red crosses in C. Then we can overlay that during training with the detections of the domain experts, which are the green circles, and end up with a set of two different kinds of surface features. E, on the right side, are the surface features we're actually interested in, we want to detect and measure, and D are false detections produced by the image processing method before. So now we want to train a classifier to differentiate these two subsets of features. To do that, we can not only use a pixel value at the exact location of one of these features, but we have to take the surrounding of the feature into account. So what we do is we extract a patch around the point of interest, as you can see on the right side here, and then build histograms of gray values for every subset, concatenate that, and get a feature vector. That can be done in a hierarchical manner to get a hierarchical histogram of gray values. In addition, we extract local binary patterns, gradient histograms, and some other features which describe these patches. So for our purpose in the summer school, we end up with a feature vector of a given length of several hundred features which somehow describe these points of interest. Before actually extracting these features, the patches are also normalized so that we can differentiate, so that we can actually generalize between features in bright sunlight or in the shadow. Then we did a test on two different flyby missions. One was flyby mission at Temple 1, where we had 72 frames, and on Hartley 2, where we have 47 frames. What you can see nicely actually on the right side for Hartley 2, you actually can see also the coma of the asteroid, so the outgassing at the bottom. So we want to have a method which does not respond, for example, to these bright areas at the bottom, but actually measure something on the comet itself. So here you can see the flyby of Temple 1. In red circles you can see the labels of the domain expert. So these are the features we are interested in. They are very faint in this case. So what we did now is we used the machinery presented in the previous module and trained a random forest classifier based on the samples from Temple 1. And then we applied it to all examples on Hartley 2, which is our training, which is our external test set, which was not used for training. And what you can see now on the right side is a comparison of different classifiers with different strategies. So shown is a precision recall curve, and so every point which is closer to the top right corner is better. So we are interested in classifiers which perform well. So for comparing classifiers, we are interested in the curves around this precision recall, because for different scenarios, you, for example, want higher precision, although you would have lower recall, or the other way around. For example, in cancer research, you want to have high recall and would be amenable to lower precision because you do not want to miss cancer cases. So in this case, it's actually the other way around. Since we don't have that much time in a flyby, we are interested in measuring one or two of the surface features, but these really have to be surface features. So we are interested in the high precision area of this curve, which is more to the left. The blue curve on the top represents the result of a random forest classifier. The blue dotted curve represents the result of a random forest classifier with a sample augmentation. So normally that's a good pre-processing step during training. One would take the samples, rotate them, and flip them to get actually different kinds of samples, and also to get classifiers which are rotation invariant, for example. In this case, it did not help much. And then we compared the procedure to support vector machines with Gaussian kernel. And random forest consistently outperforms support vector machines for that scenario. If we do it actually the other way around and we train our random forest on surface features from Hartley 2 and then classify Temple 1, the prediction accuracy is much worse. One reason is that the features on Hartley 2 are very dominant and the one on Temple 1 are very faint. So what that example shows is that in practice you would like to have a much larger training set. So in, for example, in computer vision, where we want to do classification of images, we normally have data sets of millions and millions of examples, for example, from Google search or from Flickr and so on. In space exploration, unfortunately, we do not have that luxury. So we are striving to have methods which can do well on a very small set of features, because we just have a few flybys of asteroids by now. But also in that example, random forests again consistently outperform support vector machines. Another application at JPL of random forests is for terrain classification. In this case, the samples are not surface features, but are actually the pixels in an image. What you can see here on the bottom left, the two images on the bottom left are images from the Opportunity rover, which is still roving Mars and actually just got a record of more than 40 kilometers. So that's the vehicle which drove most on a different planet. And driving on Mars, as you can imagine, is quite dangerous. Spirit, for example, got stuck, so you want to differentiate dangerous areas from not so dangerous areas. For example, sand dunes from bedrocks or gravel. What we have in addition on Mars, from the Mars rovers, are 3D maps. At the top you see a point cloud produced from the stereo cameras on Opportunity, and you can see the ripples of the dune in 3D. So and what we are now doing is we build models based on random forests where we actually take all these feature modalities into account. So the model is trained based on the grayscale navigation camera image, based on the 3D range image, based on gradients from 3D and from image gradients, and so forth. And what you can see in the bottom is a classification for dune crests in red and bedrock in green on the bottom left. In the bottom center, the differentiation is between sand dunes, and rocks. So currently that software is used on the ground to help rover planners plan the course for the next day, but in the future we most likely at one point will have good enough hardware actually on these rovers to do these vision experiments with machine learning methods like random forest on Mars autonomously. So the classification setup is as follows. On the top left you see the original image from Opportunity. Then we have training labels from a rover planner, so who is an expert in the domain classifying bedrock and dune crests. Then we train two different classifiers in that case to recognize these classes, C1 and C2. And then what you can see in the center are the probability maps. So that's the belief of the forest in every pixel of the image, how probable it is that it belongs to one of the class. At the top it's bedrock, and at the bottom it's dune crests. And then we can combine that output as shown on the right, which is then the final data product, which shows an overlay of the classification of NavCam imageries of Mars. In the long run, we want to semantically label that data, so the rover should really understand what it is, on what side of a dune it is, for example. Different sides of dunes are differently dangerous. Or if these are embedded rocks which could endanger the wheels of the rover, or if these are loose rocks which are no problem to drive over. Thank you.